Hello. Throughout human history, one of the most decisive forces on the thin line between life and death has been poison. Sometimes it was the most effective weapon of a hunter, sometimes the silent enemy of a king, and sometimes the starting point of revolutionary medical discoveries. Drops sliding from the fangs of snakes, chemical compounds hidden in leaves, and modern toxins synthesized in laboratories. All of them have been both threats and sources of hope in humanity's struggle to survive. In this journey, poison has not only brought death, it has also triggered the birth of antidotes and medicines. Now, let us explore together this story that stretches from the dark face of nature to the light of science. What is poison? Defining life-threatening substances. Poison is a toxic substance that causes structural or functional disturbances in a living organism and may be lethal when taken in a certain dose. Yet, this definition is not as simple as it seems, because almost every substance, even water, can become toxic above a certain dose. What makes something a poison is not only its chemical structure, but also the dose, the route of exposure, and the organism's response. Poisons can enter the body through chemical, biological, or physical routes. They may be swallowed, inhaled into the lungs, absorbed through the skin, or directly injected into the bloodstream. Once inside, they can damage cell structures, inhibit enzymes, block nerve transmission, or paralyze the functions of internal organs. Some poisons act almost immediately. Others accumulate slowly and exert their effects over time. Poison classification covers a wide scientific landscape. In broad strokes, we can speak of biological poisons, toxins, venom from snakes, botulinum toxin, fungal toxins, substances produced naturally by living organisms. Chemical poisons, elements or compounds such as lead, arsenic, cyanide, and mercury. Synthetic poisons, pesticides, nerve agents, industrial toxins. Each group has different mechanisms of action, and these differences are critical in determining appropriate treatments. The effect of a poison depends on the type of substance, the dose, the duration of exposure, and many individual factors such as age, body weight, metabolism, and overall health. The same substance may be harmless for one person and lethal for another. For instance, peanuts are perfectly safe for many people, yet can cause severe allergic reactions in others. The notion of poison is therefore always contextual. Poison does not only harm bodies. Throughout history, it has also been a tool of power, control, and war. Poison is invisible, silent, and often leaves few traces. It is thus not only a biological substance, but also a cultural symbol, a political tool, and a historical threat. To understand poison is not just to recognize danger. It is to understand limits, dosages, and the delicate conditions that allow life to continue. The line between life and death is, more often than not, a matter of only a few milligrams. From antiquity, to modern chemistry, a brief history of poisons. Poisons are a dark yet indispensable part of human history. They are not merely deadly substances, but symbols of fear, power, intrigue, and sometimes remedy. Tracing poisons from antiquity to the present reveals not only scientific development, but also the shadows of human nature. The earliest known poisons came from nature: toxic plants, mushrooms, and animal venoms. Egyptian, Akkadian, and Chinese healers observed and recorded the lethal effects of certain substances. Ancient Egyptian papyri describe, in detail, the deadly properties of snake venom and mixtures containing lead. Poison was not used only in the search for healing. It also served as an instrument of assassination, torture, and execution. In ancient Greece, the physician Hippocrates argued that poisons could be both agents of disease and tools of therapy. Following him, Galen experimented with using small doses of poisons to build resistance. The idea of the antidote emerged in this context. Mithridates VI, king of Pontus, is said to have taken small daily doses of poison to protect himself from assassination. The term Mithridatism is derived from his name. Among the most famous historical figures associated with poison is the philosopher Socrates, who was sentenced to death in 399 BCE by drinking hemlock. This episode shows that poison functioned not only as a weapon of murder, but also as a legally sanctioned method of execution. By the Middle Ages, the art of poisoning had begun to resemble a specialized science. In Italy, the Borgia family became notorious for using poison in court intrigues. In France, the affair of the poisons shook the royal court. Arsenic was called inheritance powder because its victims were often wealthy individuals with estates to be claimed. With the Renaissance and the rise of chemistry, poisons began to be studied more systematically. The physician-alchemist Paracelsus famously declared, "All things are poison, and nothing is without poison. Only the dose makes a thing, not a poison." This statement laid the foundations of toxicology and drew attention to the thin line between remedy and poison. In the 19th and 20th centuries, synthetic poisons produced in laboratories became tools not only for individual crimes, but also for mass warfare. Chlorine and mustard gas, used during World War I, opened the door to modern chemical warfare. During the Cold War, poisons became instruments of espionage and covert operations. The assassination of Bulgarian dissident Georgy Markov with a ricin-tipped umbrella gun is a striking example. Today, poisons remain a threat, but they are also part of modern therapy. From cancer drugs to painkillers, many medications can become toxic when overdosed. Modern toxicology is therefore not only concerned with identifying poisons, but also with understanding them and, when possible, turning them into life-saving tools. Mechanisms of poisoning: how poisons act in the body. The danger of a poison depends not only on what it is, but also on how it interacts with the body. Poisoning is the disturbance of an organism's normal biological functioning by an external substance. This disturbance can begin at the cellular level and progress to systemic collapse. Each poison has its own preferred target. Some paralyze the nervous system, others interfere with blood clotting, and some lead to organ failure. Major systems affected by poisons include nervous system neurotoxins. Substances like lead, cyanide, and botulinum toxin disrupt the electrical communication of neurons. They can cause muscle paralysis, seizures, or respiratory arrest. Cardiovascular system. Poisons may increase or decrease heart rate. Digitalis-like toxins disturb heart rhythm, while arsenic damages blood vessel walls and affects circulation. Liver and kidneys. The body's detox centers are often the most damaged organs. Acetaminophen overdose can destroy the liver. Ethylene glycol, antifreeze, can cause kidney failure. Blood. Hematotoxins. Some snake venoms destroy blood cells, prevent clotting, or trigger internal bleeding. Respiratory system. Gaseous toxins like carbon monoxide enter via inhalation and prevent cells from receiving oxygen, rapidly causing loss of consciousness and possibly death. Poison action generally follows several stages. Absorption, entry into the body, orally through the skin, via inhalation or injection. Distribution, transport of the poison via the blood to organs and tissues. Interaction, chemical reactions with cell membranes, enzymes, or receptors. Metabolism, transformation in the liver, which may detoxify the substance or, in some cases, convert it into an even more toxic form. Elimination, removal via kidneys, lungs, sweat glands, or intestines. Some poisonings cause rapid acute effects. Others are cumulative. Cyanide can be lethal within minutes, whereas heavy metals like lead may accumulate over months or years, leading to developmental delays and neurological damage in children. Individual factors, genetics, age, sex, pre-existing diseases, and concurrent medications determine why the same toxin can affect different people very differently. Toxicology thus studies not only substances but also susceptibility. Poisoning is, in essence, the chain reaction triggered inside the body by something that may appear harmless from the outside. Behind each toxic molecule lies a stealthy assault on the fragile balances of biology. Silent killers in nature. Toxic plants, animals, and fungi. Nature hides deadly secrets behind its beauty. Some plants, animals, and fungi produce potent poisons for defense or hunting. These substances can be so powerful that microscopic doses are enough to kill. Such organisms have been among humanity's oldest enemies, and at the same time, important sources of insight for medicine and science. Toxic plants. Plants can be deceptive in their appearance. One of the most infamous is hemlock, the plant that killed Socrates in ancient Greece by causing paralysis of the nervous system and respiratory failure. Atropa belladonna, deadly nightshade, is so toxic that just a few berries can kill an adult. Foxglove species containing digitalis affect heart rhythm, In carefully controlled doses, this compound is used medicinally, yet, in excess, it is lethal. Venomous animals. In the animal kingdom, venom is more often a tool of defense and hunting than aggression. Venomous snakes, such as cobras and vipers, inject toxins through their fangs. Certain frogs, especially poison dart frogs from South America, secrete alkaloids through their skin that deter predators. Scorpions, spiders, and jellyfish can also pose serious danger to humans, with venoms that target the nervous system. The venom of some snakes, like the inland taipan, is powerful enough to kill a person within minutes. Poisonous fungi differences between edible and poisonous mushrooms are often subtle and not easily recognized. One of the deadliest species is Amanita phalloides, known as the death cap. The amatoxins it contains cause irreversible liver damage. Many toxic mushrooms begin with mild symptoms like nausea and vomiting, but within hours can progress to liver failure. This delayed effect makes diagnosis and treatment particularly challenging. Defense, strategy, and evolution. Why are these organisms poisonous? From an evolutionary standpoint, toxin production is a strategy to deter predators or to efficiently subdue prey. Yet defenses shaped by millions of years of evolution can become lethal hazards for humans. In wild environments, virtually any unfamiliar organism or plant should be considered a potential threat. Nature as a teacher. Paradoxically, natural poisons have played a major role in drug development. Painkillers derived from frog toxins or anticoagulants derived from snake venom show how nature's deadliest molecules can be redirected to save lives. The silent killers of nature are not only threats, they are also evidence of nature's complexity and of biological engineering at its finest. To know them is both to protect ourselves and to learn. By human hands, assassination, war, and chemical poisons. Natural poisons were originally environmental hazards. Over time, however, humans learned to refine, concentrate, and design poisons, turning them into deliberate instruments of power. Poison ceased to be an accidental threat and became a chosen weapon. From assassinations and battlefields to covert operations and mass atrocities, chemical agents have left a deep stain on history. The art of assassination. Many political leaders and dissidents have been targeted by hidden poisons. In ancient Rome, specialists in poisoning were especially prominent among the aristocracy. In the Middle Ages, the Borgia family became infamous for serving poisoned food and drink. Arsenic, tasteless and odorless, emerged as the poison of kings or inheritance powder, quietly eliminating inconvenient relatives. In the modern era, poisoning became part of intelligence warfare. During the Cold War, some assassination operations relied on microdoses of exotic toxins. The killing of Bulgarian dissident Georgy Markov in London with a ricin pellet injected via a modified umbrella is one of the most notorious examples. In more recent times, VX nerve agent has been used in high-profile assassinations, such as the killing of Kim Jong-nam. The Dark Age of Chemical Warfare, World War I, marked humanity's first large-scale encounter with chemical warfare. Mustard gas, chlorine, and phosgene injured and killed hundreds of thousands of soldiers, often leaving survivors blinded, scarred, or disabled for life. Gas masks emerged, but were not always sufficient. Poison gas had transformed the battlefield into a chemical laboratory of suffering. In response, the 1925 Geneva Protocol banned the use of chemical weapons, though not their production or stockpiling. During World War II, Nazi Germany developed nerve agents such as tabun, sarin, and soman. These were not used on the battlefield, but became the technological basis for future chemical arsenals. Terrorism and toxic fear. The 1995 sarin gas attack in the Tokyo subway by the Aum Shinrikyo cult showed that chemical agents could become tools of urban terrorism. Sarin, which can be produced without the full infrastructure of a modern state, spread panic and death in a matter of minutes. A weapon that sends a message today. Chemical poisons are not only weapons of war, but triggers of diplomatic crises. State-sponsored poisonings of ex-spies and dissidents, violations of chemical weapons conventions, and clandestine nerve agent programs remain major international concerns. Poison in this context does more than kill. It sends a message, spreads fear, chooses specific targets, and often leaves ambiguous traces. In the modern world, poison has become the craft of killing without pulling a visible trigger, a nightmare disguised in the language of science. The birth of antidotes. Reverse chemistry and medical intervention. If poison kills, antidote saves. This simple equation lies at the heart of humanity's long struggle against toxins. Antidotes are not just chemical formulas. They are vital solutions born from the fusion of nature and science. Every antidote grows out of an attempt to understand how a particular poison works. Toxicology, therefore, is not only the science of danger, but also the art of turning that danger back on itself. Ancient antidotes, Mithridates, and the first experiments. The idea of antidotes goes back to antiquity. As legend tells it, Mithridates VI of Pontus tried to protect himself from assassination by taking small daily doses of poison to build resistance. This practice, known as Mithridatism, is one of the earliest conceptual roots of antidote thinking. The complex mixture called Mithridatium, attributed to him, was used in various forms for centuries. Modern antidotes, counteracting the molecule. Modern antidotes generally work in three main ways, depending on the poison's biochemistry. Neutralization, directly binding and inactivating the toxic molecule. Example: antivenoms contain antibodies that bind snake or scorpion toxins. Receptor blockade, preventing the poison from binding to its target receptors on cells. Example: atropine blocks acetylcholine receptors in organophosphate, pesticide poisonings. Enhanced elimination, accelerating metabolism or excretion of the toxin. Example, N-acetylcysteine, NACE, helps the liver detoxify acetaminophen overdose. Antivenom production, life from venom. Antivenoms used against venomous snakes, scorpions, and spiders are the products of a sophisticated biotechnological process. Small doses of venom are injected into animals with robust immune systems, typically horses. The animals produce antibodies against the venom. These are later extracted, purified, and turned into antivenom. Because they are derived from animal proteins, antivenoms carry a risk of allergic reactions, so dosing and administration require caution. Chemical antidotes and industrial poisonings. Special antidotes have also been developed for laboratory and industrial toxins. Hydroxycobalamin, a form of vitamin B12, is used in cyanide poisoning. Methylene blue is used in certain types of methemoglobinemia, and specific chelating agents help remove heavy metals like lead or mercury from the body. Poison teaches its own cure. Every antidote exists because the poison behind it was studied in detail. Developing an antidote is a kind of reverse engineering. First, scientists learn what the toxin does. Then they search for ways to interrupt or reverse its effects. This makes antidote research one of the most strategic branches of toxicology. Yet, not every poison has an antidote, and no antidote is universally suitable. Body structure, allergies, dose, and timing all determine whether treatment will succeed. Modern toxicology therefore combines antidotes with diagnostic tools, imaging, rapid tests, and individualized treatment protocols. An antidote is not only a molecule, it is a lifeline of hope. Sometimes that line is measured in minutes, sometimes in milligrams, and once it is crossed, there may be no way back. The science of toxicology, dose, effect, and rescue. Everything is poison. Nothing is without poison. Only the dose makes a thing, not a poison. These words, from Paracelsus, the father of toxicology, capture the essence of the discipline. Toxicology stands precisely on this fine line, understanding the relationship between dose and effect, and learning how to intervene. The power of dose, from harmless to lethal. Toxic effects depend very often less on what is taken than on how much. Even basic substances such as sodium, salt, or water can cause toxic effects if consumed excessively. Toxicology therefore evaluates not just what is given, but how much, how, and how often. Dose-response relationships are typically represented as curves. Below a certain threshold, there may be no observable effect. Above that threshold, effects intensify and may eventually become lethal. These curves allow scientists and clinicians to predict risk and plan treatment. Routes of exposure. Where does the poison enter? A toxic substance may enter the body in several ways: orally, via the skin, through inhalation, or by injection. Each route leads to different absorption speeds and patterns of damage.
Cyanide gas can cause death in minutes when inhaled, while certain pesticides absorbed through the skin act more slowly but can cause severe damage once accumulated. Target organs. Where does the poison strike? Toxins often prefer specific targets. The nervous system, liver, kidneys, and heart are among the most vulnerable. Toxicology therefore analyzes not only the substance itself, but also which organs it attacks and how. Whether a poison is primarily neurotoxic or hepatotoxic, for instance, directly shapes the treatment strategy. Biological half-life and clearance. The persistence of a toxin in the body is measured by its biological half-life. Some toxins are cleared within hours, while others linger in tissues for weeks, months, or even years. Heavy metals such as lead may accumulate in bones for decades, sometimes leading to chronic poisoning. Therapeutic strategies. Science in the service of rescue treatment in toxicology typically proceeds on three fronts: cutting off the source, preventing further absorption with measures such as gastric lavage or activated charcoal when appropriate, neutralizing the effect, using specific antidotes or symptomatic treatments to restore physiological balance. Supportive care, providing respiratory support, stabilizing fluid and electrolyte balance, and protecting organs at risk of failure. These interventions often race against time. Many toxic reactions are reversible in the early stages, but cause irreversible damage if treatment is delayed. Risk assessment and prevention. Toxicology is not only about handling emergencies. It also evaluates food additives, drug doses, environmental chemicals, and occupational exposures. Through risk analysis, labeling regulations, and public education, it protects communities long before an actual poisoning occurs. In this sense, toxicology acts as a shield between humanity and its own creations. Those who understand dose, effect, and timing, and who know how to intervene, are the practitioners of this vital science. Modern emergency response, antidotes, antivenoms, and protocols. In poisoning cases, medicine enters into a direct race against time. Within minutes or even seconds, vital systems can begin to fail, and appropriate intervention becomes the decisive factor between life and death. Modern emergency care brings together toxicology, rapid diagnostics, and carefully crafted protocols to meet this challenge. What is an antidote? Matching poison. With counterpoison antidotes are pharmacological agents that block or neutralize the effects of specific toxins. Not every poison has an antidote, but for many common toxins, effective agents exist. For example, atropine, used in organophosphate and pesticide poisoning. N-acetylcysteine, NABs, prevents liver damage in acetaminophen overdose. Hydroxycobalamin, a vitamin B12 derivative used in cyanide poisoning. Naloxone, reverses respiratory depression caused by opioid overdose. These drugs act not only at the chemical level,
but also by stabilizing vital physiological functions. Serums and antivenoms, living solutions to living venoms. Antivenoms used against snake, scorpion, and spider bites are immunological products. Animals such as horses or sheep are injected with small amounts of venom. Their immune systems produce antibodies, which are then collected from their blood and purified. The resulting antivenom binds to venom molecules in the patient's bloodstream and neutralizes them. However, because these products are derived from animal proteins, they can trigger allergic reactions. For this reason, dosing and monitoring must be done with great care. Emergency protocols, a systematic approach to rescue. In clinical toxicology, treatment usually follows a three-stage protocol. Initial stabilization, O. Ensure airway patency, A. Airway, O. Assess breathing, B. Breathing, O. Evaluate circulation, C. Circulation, supportive care, O. Oxygen administration, and, if necessary, intubation, O. Correction of fluid and electrolyte imbalances, O. Continuous monitoring of neurological status and vital signs, specific therapy, O. Identifying the toxin, history, lab tests, context. Selecting the appropriate antidote or antivenom, O. Observing for side effects and complications. Rapid tests and poison control centers. Quick diagnostic kits help detect certain toxins in blood or urine, allowing faster, more targeted treatment. Many countries also maintain 24/7 poison control centers that provide guidance to healthcare professionals and the public about suspected poisonings. Training, preparedness, and systems. The effectiveness of emergency care depends heavily on the training of medical personnel. In areas where snake bites or agricultural toxin exposure are common, mobile antidote kits and well-rehearsed protocols can be life-saving. Modern medicine saves lives not only through knowledge, but also through organization, planning, and preparedness. The better these systems function, the more quickly the power of poison can be broken. Poison or medicine? The dose that draws the line. The same substance can save a life at one dose and end it at another. This apparent contradiction lies at the heart of pharmacology. In truth, there is no rigid boundary between poison and drug. That boundary is drawn by the dose. Paracelsus's principle: the dose makes the poison. In the 16th century, physician-alchemist Paracelsus summed up this paradox with a sentence that still defines toxicology: sola dosis facit venenum. Only the dose makes a thing a poison. In other words, even the most benign substance can become dangerous when taken in excess, while very dangerous substances can become useful medicines when administered in the right way and quantity. Pharmacodynamics and the therapeutic index. A core concept in drug development is the therapeutic index, the ratio between the dose that produces desired effects and the dose that produces toxicity. The wider this safety margin, the safer the drug. Some powerful medications, such as chemotherapy agents, lithium, or digoxin, have narrow therapeutic indices and therefore require careful dose adjustment and monitoring. Dose-response curves, mapping effect. Toxicology and pharmacology use dose-response curves to define the range in which a substance is effective and the range in which it becomes harmful. These curves are crucial in determining optimal therapeutic doses and estimating the risk of poisoning. From poison to drug. Many drugs were initially known as poisons. Botulinum toxin, Botox, one of the most potent neurotoxins known, yet at minute doses, it is used to treat muscle spasms and certain neurological disorders. Digitalis, from foxglove, supports heart function in heart failure, but in excess can stop the heart. Arsenic, once used experimentally to treat syphilis, though long abandoned due to toxicity. These examples highlight humanity's ability to domesticate dangerous substances and turn them into therapeutic tools. Daily life and the dose paradox. Dose matters not only for medications, but also for food and supplements. Vitamin A supports immune function, but in large amounts can damage the liver. Iron supplements are vital in anemia, yet overdoses, especially in children, can be fatal. Context and individual variation. Dose is not an abstract number. It operates in a living body. Age, weight, genetics, liver and kidney function, and metabolic rate all determine how a given dose will act. The same pill can be safe for one person and dangerous for another. This is why modern medicine increasingly speaks of personalized dosing. Ultimately, the difference between poison and medicine is both a subtle art and a precise science. Used in the right amount, knowledge heals. In excess, it can harm or kill. Survival knowledge. What to do in case of poisoning? Poisoning usually occurs suddenly and can easily trigger panic. In such moments, calm and correct actions can make the difference between life and death. What is needed is not only theoretical knowledge but also practical reflexes, knowing when and what to do. Identify the source. The first step is to determine what the person was exposed to, as quickly and accurately as possible. Was a medication taken in excess? Were toxic mushrooms eaten? Was there contact with a chemical? Was the person bitten or stung by a snake or insect? The type of exposure directly shapes the necessary response. If possible, bring the product packaging, a photo of the plant or animal, or any other evidence to medical professionals. Call for emergency help. Delay can be fatal. If poisoning is suspected, emergency services and, where available, a poison control hotline should be contacted immediately. Provide age, sex, and approximate weight of the person. Name of the substance, if known. The estimated amount and time of exposure. Current symptoms: nausea, dizziness, confusion, breathing difficulty, etc. Do not induce vomiting on your own. One of the most common mistakes in household poisonings is forcing the person to vomit. Certain chemicals, acids, alkalis, hydrocarbons, can cause additional damage when vomited back up the esophagus. Vomiting should only be induced if specifically recommended by medical staff. Check consciousness and breathing. If the poisoned person is unconscious, breathing and pulse must be assessed. If there is no breathing, start CPR, chest compressions, and rescue breaths. If the person is breathing but unconscious, place them in the recovery side position to keep the airway open and reduce risk of aspiration. Activated charcoal, a first line of defense? Activated charcoal can reduce absorption of certain orally ingested toxins by binding them in the gut. However, it is not suitable for all poisons and may be harmful in some situations. It should be used only under medical guidance. Skin and eye contact. Rinse thoroughly. If the toxin has come into contact with the skin, remove contaminated clothing. Rinse the affected area with plenty of water for at least 15 minutes. If the eyes have been exposed, they should be kept open and flushed with clean water for an extended period. Snake or insect bites. What not to do. Keep the bitten area still, and keep it below heart level if possible. Do not apply a tourniquet. Do not cut or suck the wound. Gently cover the site and keep the person calm. Panic and physical exertion can accelerate venom spread. Prevention. Knowledge before crisis. Most poisoning incidents are preventable. Therefore, keep cleaning products, medications, and pesticides out of children's reach. Do not consume wild mushrooms or plants unless you are absolutely certain of their identity. Post local emergency and poison control numbers in a visible place at home. Consider basic first aid training and share safety knowledge with family members. In the end, in a poisoning event, accurate information and prompt action are far more valuable than panic. The nature of poison is complex, but the power that neutralizes it is human knowledge. An informed individual protects not only themselves, but also everyone around them. Poison has always been a test for humanity, a symbol of fear, death, and the unknown. Yet it has also been a teacher of science, discovery, and survival. Every drop of poison carries within it both threat and cure. This dual nature reminds us of life's fragility and the power of knowledge. Today, thanks to antidotes, toxicology, modern emergency medicine, and well-informed societies, we are able to overcome even the darkest faces of poison. For the line between life and death is sometimes razor-thin, measured in a breath, a drop, or a dose. As humanity learns to walk that line, it gains not only the ability to survive, but also a deeper understanding of nature, of science, and of its own vulnerability.